All right, guys. So in this video, we're going to be going over energy and chemical change, specifically thermodynamics, and kind of what the concept is on calorimetry. So if you haven't watched any of the other notes provided, this is just kind of a brief overview of the key terms that you want to make sure you're able to understand and really be familiarized with. The main thing that this is going to focus on today is going to be about really heat. And you got to be at least familiarized with the term, what is the difference between heat and temperature? So temperature measures kinetic energy. Heat is energy that flows from a warmer substance to a cooler substance. So I'm going to start off this little presentation by just kind of explaining how that works and how you should be able to visualize what's happening here. So this is a FET that deals with energy. So if I reset all of this, you should be able to see a few different things. So this will kind of tie in the difference between how energy flows as well as temperature, right? So let me just put some water on this bucket, and you can see that if I'm adding in heat, I'm also adding in energy, right? You can see those little E's are flowing into the water. Now, if I put this thermometer in, it's measuring how fast those water particles are actually moving. So the faster that those things are moving, the higher my temperature is going to be. So understand the definition between them, that the faster your molecules are moving, the higher your temperature is. So temperature is a measure of kinetic energy. Now, if I took this and cooled it down, watch what happens. If I put this beaker of water on ice, notice where energy is flowing. Energy always wants to go from a warmer substance to a cooler substance. So you can see that those energies are actually flowing from the water down to the ice. So energy is leaving. It's going from the water actually into the ice. So energy flows from a warmer substance to a cooler substance, okay? Now, this one is, I'm actually gonna reset these both. And I'm gonna put water and iron on these together. Now, I'm gonna show the energy symbols. I'm also going to add thermometers on both of these, okay? So I can take this thermometer here, I'm gonna put a thermometer in water, and I'm gonna link these heaters together. So just watch what happens when I heat these things up at the same time, and take a look to see which one is gonna increase in energy absorbance faster, as well as who's increasing the temperature quicker. So watch what's going on here. If you notice, I'm continuously adding heat, right? I'm adding energy. But if you look at the iron brick here on the left, notice that that's gaining temperature. The temperature is rising a lot quicker. It's able to absorb energy a lot faster, okay? So let's kind of dive into what this looks like. So really what you should notice now is when you think about the concepts, right? Heat is the energy that flows from a warmer substance to a cooler substance. The more energy something has, the more likely it is that their kinetic energy of those particles are going to increase, right? So temperature is a measure of those kinetic energy. So one thing that we need to understand is how heat is going to be measured. And this is going to be something specific, right? 1 calorie, like a food calorie, as well as 4.184 joules. That's going to be the unit of heat. Specifically, we're going to be working a lot here with joules. So this is a conversion factor you should be pretty familiarized with in terms of converting units and know the specific heat of a couple of different substances. So one thing that you need to for sure also be able to understand is the specific heat. So I'm not going through in a whole lot of detail. Please watch Ms. Toth's notes on those for sure. This is just kind of getting the big concepts dialed in. So we need to mention specific heat. So the specific heat is the amount of heat required to raise the temperature of 1 gram of substance by 1 degrees Celsius. So if you go back to this FET, what you should be able to put together is, as I heat these things up, did you notice that the iron brick is able to absorb energy a lot easier? It has a pretty low specific heat where water is a lot higher. And so to put this simply, it takes a lot more energy to change the temperature of water because water has a really high specific heat. So what you're seeing is that it takes some energy for water to actually absorb that energy and increase the temperature by 1 degree, okay? Whereas iron has a really low specific heat, okay? And I can even play around with this too. Watch if I'm gonna stop linking the heaters and I'm just gonna cool down water. And so we can kind of take a look at a few things here that should help you out conceptually, at least in terms of what's going on when we look at how energy flows. So I cooled down my water, notice that the energy is leaving. what's interesting is I'm going to take this iron brick with this pretty high temperature. Actually, before I put it in, I'm going to add as much energy as I can to this. So the temperature here is relatively high. And watch what happens. When I put this iron brick into the water, watch what happens. The temperature of the brick declines super quick. The temperature of the water went up a little bit, but again, remember, water has a high specific heat. It takes a lot of energy to do that. Why did the iron brick change temperature so quickly? Well, it has a lower specific heat than water does. So when we're jumping into this, one key thing that we should be familiarized with when we're doing this is calorimetry. We're going to use a calorimeter. So that's going to measure the heat that is absorbed or released during a chemical reaction. So really, this video is going to focus on how do we measure specific heat, how do we calculate heat of a reaction. There's a couple of key things here about this that we need to make sure you feel comfortable with. So if we were in class, one lab that we would be doing is this lab on calorimetry. So what that means is that you're going to be looking at the heat that is absorbed or released during a chemical reaction. So one key thing that we need to get dialed in before we do any calculations is these terms exothermic versus endothermic, okay? So exothermic means heat is going to be released during the equation or the reaction, I should say. Endothermic means heat is going to be absorbed. So if the final temperature is greater than your initial temperature, that means something was mixing and your final temperature was increased because some heat from the reaction went out into the water, okay? Now, if you had an endothermic reaction, because all of these typically are done in a aqueous solution, meaning they're with water. So that means energy from the water actually is absorbed. So when you think about this, you need to understand that water, and I'll jump back to this FET just to kind of emphasize this point again. You can see that water, even when I cool it down, even if it's at, let's say, room temperature, it still has energy, right? So energy can be essentially taken from water and going into a reactant. And then that's what we're looking at too when we think of if it's endothermic. A lot of students get confused and they're thinking, well, where is this energy coming from? I didn't put it on a flame or anything like that. Why did the temperature change? A lot of people forget that water still has energy. Even at room temperature, it can actually absorb some heat from the water, okay? Now, the biggest calculation that we're going to be looking at is this Q equals MC delta T. And again, Ms. Toastnotes do a great job explaining how to calculate this. But for us, really, we're just reviewing kind of what's going on with Q. So the heat absorbed or released is going to be Q. M is the mass of the water. And we're looking at water a lot in these calcs. So one helpful thing to remember is that 1 milliliter of water is equal to 1 gram. So a lot of people just get confused where it asks, well, it gives you 200 milliliters of water. Just be on the lookout. You have to convert that to grams. So this C with a little p next to it, the specific heat capacity for water, okay? Now, this is not something that's going to be blatantly given to you in a practice problem. You do have to memorize it, or you just have to look back here. Remember, the specific heat for water is 1 calorie per gram degree Celsius, or 4.184 joules per gram degrees Celsius. Okay, so this is how much energy it takes for water to change the temperature by 1 degree Celsius. Okay, now again, water has a pretty high specific heat. The reason why, if you think back to the intermolecular forces, those hydrogen bonds, it takes a lot of energy to break all those hydrogen bonds. So in terms of that, let's look through this practice problem first. I'll show you the simulation, and then we'll do one more simulation to kind of help drive this point home. So this first one, and it's going to be almost identical to the one in the other video notes, but it says calculate the amount of heat in kilojoules released by a reaction that caused 250 grams of water to increase in temperature from 21 degrees to 76 degrees, okay? So basically, we're going to follow through with this equation. The Q equals MC delta T. And just to remind you that your delta T is going to be your temperature final minus your temperature initial. So our delta T, we got to solve for that one first. It's going to be 76.0 degrees Celsius minus 21.0 degrees Celsius. And so our overall change in temperature is going to be 76 minus 21 is 55.0 degrees Celsius, okay? Now M, we already have this figured out where M is the mass of water. So let's just go ahead and plug this in. Now it's asking for it in kilojoules, so you have to be careful on figuring out what you're solving for. So the specific heat, you have a choice here. So we got to make sure we select the right specific heat we want to use. So the specific heat, we could either use 1.00 calories per gram degree Celsius or 4.184 joules per gram degree Celsius. I'm actually going to use this one. The reason being is because it's asking for it in kilojoules. So you want to be careful on understanding why I'm doing that. So I'm just going to go ahead and plug this in and solve for my heat. So in terms of this, I have 250.0 grams. That's my mass of my water. My specific heat that I'm using is 4.184 joules per gram degree Celsius. And my delta T is 55.0 degrees Celsius. So plugging this all in, let's double check with sig figs. I have 3 here, I have 4 here, so I'm gonna have 3 in my final answer. So I'm just gonna quickly solve this for us. 250 times 4.184 times 55. I got an answer of 57,530. Now let's cancel our units out. Grams cancel, degrees Celsius cancel, and I'm left with joules, okay? Now, I have to have this in kilojoules because that's what it's asking. So I'm going to move my decimal place 3 to the left over. So my final value of Q would actually be 57.5 kilojoules. All right. So basically what this means is that is the amount of heat that was absorbed. Okay. So to kind of conceptualize this and put this together, I can show you this whole thing again, right? So basically what you were looking at is if I added a substance, right? If I heated up, let's say a piece of iron, and I actually put this in, what we were actually measuring, let's put it that way. What you were measuring just now was how much energy did water absorb doing that change in temperature. So the temperature of water actually goes up. So not a lot in this simulation, but according to the problem, really that's what you were looking at. So you added a substance and it changed the temperature of the water, an increase from 21 to 76.0 degrees Celsius. So that's kind of what you're looking at. You're looking at measuring how much energy is absorbed. And that's what that FET does a good job explaining, okay? Now, that kind of leads into where we get into thermochemistry. Now, this chemistry is not just about adding a piece of metal to a substance and measuring how much it increases the temperature of water by, as cool as that might sound. A lot of times we mix solutions together, and that's going to help us determine the actual enthalpy, which is the heat of a reaction, okay? And so this is where things get a lot more specific. So thermochemistry is where we're going to study the heat of changes in a chemical reaction. And our focus really is going to be on enthalpy, okay? Now, enthalpy is this delta H. So I should say H is what we use to represent enthalpy. But one thing that we look at in an overall equation is your change in enthalpy, okay? And so to do that, we're going to look at how much heat do we have at the beginning and how much at the end. So your enthalpy of your product minus your enthalpy of your reactants, that's going to give you your overall delta H. Okay. Now, the reason why you should really care about this delta H value is to help you figure out if something is going to be endothermic or if it's going to be exothermic. Okay. So this is kind of a brief snapshot of the notes given. So if it's exothermic, that means heat is going to be released. So for example, if I took sodium hydroxide and hydrochloric acid, like if I had those two solutions and I mixed them, I'm actually going to be releasing 12 kilocalories of heat. So remember, that's a heat term. And really what you're looking at here is that you had initial enthalpy in your reactants, you have less enthalpy in your product, and you released some energy, okay? Energy got released, and one thing that you had to look at, and typically problems like really simple problems like this, if it gave you the delta H of your products and you minus your reactants, this is a number that you really care about. Not so much the number, I should say, but if it's negative or positive. So in this case, if we have what's considered an exothermic reaction, that means heat is going to be released when you actually let this reaction proceed, okay? So notice I had more enthalpy in my reactants than I did my products. So I actually went to a more stable state. And so that is something that you really want to feel comfortable with. So if you look over here, if I have an endothermic reaction, remember if I had this is my reactant, these are my products, my delta H is actually a positive value. And notice where I added my heat term in my overall equation, I left it on my reactant side. So one thing that you want to make sure you feel okay with is if it's an exothermic reaction, the key here in all of this is if it's a negative delta H value, you're putting that heat term on the products, and that lets you know that it is an exothermic reaction. Heat was released, okay? Now, if it's an endothermic reaction, you're gonna add that heat term on the reactant side. That means it actually takes energy to let this reaction proceed, okay? Now, just like I mentioned earlier, don't let this stress you out, but remember that oftentimes when we do these reactions, they're in what's considered an aqueous solution. So that means a lot of these things are mixed in with water. So understand that water is going to be our key focus on how we can figure out this delta H value, because it is a value, okay? So it's a measure of heat, okay? So we're measuring heat. So please don't forget that. And let's just kind of revisit heat is that energy that flows from a warmer substance to a cooler substance. Don't let that, don't make it more difficult than this already can become. So Q is what we're solving for. Now we're just kind of adding in, well, what does it look like on our products, on our reactants, and why should we really care about that, okay? So you need to really make sure you feel okay with these graphs. You'll see them again in both AP Chem, AP Bio, really any science class for your entire career in science will focus a lot on these graphs. So just to kind of help this make a little more sense, at least in a really simplistic way, would be when you look at something like this, well, why does energy get released and what makes it exothermic? So if I have carbon monoxide and chlorine gas, right, these are my reactants, there's an initial moment where my bonds are broken, but my product, these products, right, is actually going to be less reactive than your reactants, right? So your products are actually more stable. And the key is that energy is released by forming these new bonds. This is a more stable state than these reactants were, and that essentially gives off some heat. So your delta H is negative. So it just depends on the reactants and the product. So this is not the end all be all form, but this is just kind of a nice simplistic way, at least just something to get us started on talking about when you look at your products, if they're more stable, that's in terms of you're releasing energy. So that would be an example of an exothermic reaction, okay? Now, let me show you this simulation on how we would often do something like this in a lab. So what we're gonna look at here is just calculating the heat of a reaction. So if you had, you know, sodium hydroxide and hydrochloric acid, this is one of the kind of end all things. If you can do this, you're in pretty decent shape in terms of calorimetry, and you'll see it in what it would have looked like in a lab setting. So let's say we had 100 milliliters. Let's go through this problem and I'll kind of work you through the simulation as well. If I had 100 milliliters of 2 molar sodium hydroxide mixes with 100 milliliters of 3 molar hydrochloric acid, what is the heat of the reaction if the water changes temperatures from 20 degrees to 33.62 degrees? And that is going to be in degrees Celsius, so I should add that in as well, okay? So let me show you this simulation. It's actually really helpful if you are struggling with how this looks in a lab. So, and I'll make another video about this simulation as well, but let's just take a quick look here. So this is we're gonna go ahead and click on the experiment and we're gonna actually run the experiment right away. So basically I'm gonna have two solutions. This is gonna be a sealed chamber and it's only gonna be measuring the amount of the temperature change, right? So let me kind of put this into concepts for us to help you visually see what's going on. So let me go back here to the problem. So I'm gonna start this off and just making sure we have the right amount. So I'm going to mix in 100 milliliters of 2 molar sodium hydroxide. I'm going to choose my solution. I will do sodium hydroxide first. I will do 100 milliliters, and I'm going to set the molarity to 2 molar. Let me just verify. Yeah. So 100 milliliters of 2.00 molar sodium hydroxide is going to mix with 100 milliliters of 3 molar hydrochloric acid. So I'm going to click next. I'm going to choose my next solution. we're going to mix it with hydrochloric acid. And notice again, it says aqueous. That's what that AQ stands for. So it's mixed in with water. So I have 100 milliliters, and it was 3 molar. Let's show the specific heat. Now, pay close attention to this. Notice that the specific heat is this 4.184. This is showing the specific heat of the water, because again, water is essentially what these are all mixed in. So we're going to go ahead and click next. So now I have it all set, and we should see what's going on here. I'm going to show a graph view and show a microscopic view as well to kind of see what's going on here. Now notice my initial temperature right here is 20 degrees Celsius, just like that problem was explaining, right? So the water is going to go from this 20 degrees to, it should, and I ran this earlier, so I want to say the end temperature should be around 33.62. So let's kind of see if this is going to play out that same way. So I have my sodium hydroxide solution here. I have my hydrochloric acid solution here. And let's kind of just see and try to put this together if it's an endothermic reaction or an exothermic reaction, and how can you tell before we do the calculation side. So let's just look at the concept first. So we're going to take this solution, and now all of a sudden I have this 200 milliliter solution of water. I have my sodium hydroxide and my hydrochloric acid mixing together. Now notice the temperature of the water is actually climbing. So we're looking, and all we can really do is we can't physically measure the HCl and NaOH. We're measuring the environment that they're in. So basically the temperature of the water is increasing. So let me basically show this graph view again. Basically the temperature of the water was climbing. So let's jump back to this visual real quick and remind you guys that what you mixed in, you had if we kind of looked at it at a really small scale, what you guys saw is that right here we had NaOH plus HCl, right? And so the temperature of the water, because all we're measuring is the temperature of the water, is that the temperature of the water increased, okay? So as that temperature rose, that gives us this big indicator that, hey, this is going to be an exothermic reaction. We actually released some heat. So heat was released. When we say released, it's released into the aqueous solution. So that's one thing that I think some students struggle with initially when they're doing these problems. So you can see that when you mix these things together, there's our final temperature of 33.62 degrees Celsius. So we actually were able to kind of see this temperature rise. And let's now try to solve this thing. So this one is going to be a pretty in-depth solving. So we're going to be solving for Q, and there's going to be 4 steps involved. So let's kind of take a stab at this one. And this one will be a little bit different than the way that the first or missed host notes were, just because of what they're giving us in the problem. So let's take a look at what we should do first. First, I want to go ahead and solve for, let's figure out our temperature change. And then we'll go from there. So first I need to find my delta T, which is going to be my temperature final minus my temperature initial. So in this case, my delta T was going to be 33.62 degrees Celsius minus the initial temperature of 20.0 degrees Celsius. And when I did this earlier, I got a value of 13.62 degrees Celsius, okay? So there's my first step. I figured out that temperature change. So I'm going to keep that and just kind of jump back and forth so you can see step by step what happened, right? It was initially at 20 degrees. Now, it raised from 20 to 33.62, so it's an exothermic reaction. You should feel pretty confident on that part because the temperature rose. The next thing that we have to do, though, is we got to figure out, we have to find the moles of NaOH. The reason why I'm doing this is I set this up because HCl was in excess. So when I ran that earlier, HCl was actually in excess. So in terms of the limiting reactant, my sodium hydroxide was, okay? So how are we going to find this? It didn't give us our grams amount, So we kind of have to do a different method to figure out our moles. So let's go back to this simulation, and I want to just really focus in here. It didn't give me grams, but it did give me the molarity, and it did give me the initial volume of how much I added in. So basically what I had now is, okay, well, I know the molarity, I know the volume, I can now figure out what the actual molar amount of my sodium hydroxide is, okay? So the reason, again, why I'm doing it for sodium hydroxide is just because my hydrochloric acid was in excess. So let's figure this one out. So going back to the problem, it's just another way. Some problems will give you grams, sometimes it'll give you the molar amount. So, so for this one, we have the molarity equals to moles over liter. So in this case, molarity, we know what it is, excuse me. So we actually had this 2.0 molar sodium hydroxide. So I'm going to plug this in over here, 2.00, and I'm just going to write this out as moles per liter, equals, and again, I'm solving for moles, so moles over liters. Okay, now what is our liter amount? Well, we actually mixed in 100 milliliters, so that's going to be the same thing as actually going to be 0.100 liters. And hopefully you guys are able to understand how I would solve for moles. So I would just multiply by 0.100 liters. That cancels. And my final mole amount of NaOH would actually be equal to, and during doing this earlier, I should get a value of 0.2 moles. Okay, so I'm going to just put a box over there. All right. So that's another way of solving for it. Because I had the molarity, I knew the volume amount. So that's how many moles I had. Different problems might give you different scenarios to figure that one out. So the third thing that we're going to do is solve for Q. Q equals N delta T, right? Now, this is when you actually are going to be using water, right? So we have to use water for this step, okay? So this is something we got to be careful with. And this is realistically what you would have done in an actual lab. So you're using water. What's the mass of water? Well, you got to go back to what we did in that lab scenario. So I'm going to keep this for right now. Let me just jump you back to this, and I'll actually reset this. Let me show you the solutions that we did, right? We had sodium hydroxide. We added in 100 milliliters at 2.0 molar. So I'm going to do next. We'll just run this again. So I'm going to choose this solution of hydrochloric acid. We added 100 mils of 3 molar HCl. Okay. So check out what happens here. And I'll just show this thing again. I had 100 milliliters of this solution, 100 milliliters of this. So when we look at the overall volume of water that we had, it's actually 200, right? Because 100 plus 100 gives me 200 milliliters of water. So remember, in an aqueous solution, 1 milliliter of water is equal to 1 gram. So in terms of that, that's something that some students get a little stressed out with. So what is the overall mass of our water? So in this case, our mass of water, right? So I can put this over here. Our mass of water was actually equal to 200.0 grams, okay? So I'm going to go ahead and solve for my heat, the heat that was actually absorbed by the water, because remember we showed you earlier, the temperature of the water increased. So Q equals the mass. Now we have 200.0 grams. Specific heat in this one, I'm going to use the 4.184 joules per gram degrees Celsius. And my change in temperature, we had figured out earlier in step 1, is this 13.62 degrees Celsius. Now, when I solve this, I got a value of 11,397.216 joules. Now I'm going to quickly convert that into kilojoules, and I'm going to round at the very end for my sig fig. So this becomes 11.397216 kilojoules. All right. And so basically now what I'm going to do is I am going to take this and take this value. All right. So I'm going to figure this out in terms of kilojoules per mole. So I'm going to divide these two together. Okay. So step 4 is I'm going to figure out what my final value is. I'm going to go through this and I'll do 11.397216 kilojoules per 0.20 moles of NaOH. And now is where I'm going to round to my sig figs. Going back to what did we start with? I should have clarified this. This should have been 100 point, just to keep things all at a 3 sig fig. So I apologize for that, but it should be 100 points. So that way everything's going to be, that's not 1 sig fig. So I now would say that when I calculated this out, I got a value of 96.0 kilojoules per mole. Okay. Now, you might be thinking you're done, but the final step involved in all of this is you have to remind yourself, was this an endothermic or an exothermic reaction? So in terms of this, we got to figure out endo or exothermic, okay? Well, remember that when we did this, the temperature actually went from 20 to 33.62. So energy in this case was actually released. So you got to jump back to this. Remember, if it's exothermic, you're going to stick the negative sign in front of it. So just to finalize and get this entire problem correct, you would put a minus in front. So that lets you know that it's an exothermic reaction. So on kind of an interesting way of solving this one, the main one is that it gave you the molarity. But regardless, the key thing here was that you mixed in hydrochloric acid with sodium hydroxide, and then you saw the temperature of the water rise, and that lets you know that it was an exothermic reaction. So just a couple of simulations to kind of help you guys to work through some of these problems, just another way of seeing this, and I hope that that's helpful.